in this video, we're going to introduce chapter 30, which is on Faraday's law. If you remember in chapter 29, we said that a magnetic field can be produced from currents. And so the question that we're going to ask ourselves is, can I produce electric current from a magnetic field? So the answer to that question can be found from Faraday's law. So Faraday's law is what makes it possible for us to convert magnetic fields into electric currents. And this is called the principle of electromagnetic induction. So this is what we're going to be talking about in this chapter, chapter 30. Now, the principle of electromagnetic induction has a lot of applications, and one of the most important applications is in the generation of electricity. So one example that you see here is an example of a windmill. So these are just like blades. So energy from the wind is converted here into some mechanical energy, and so these blades are connected to a magnet. As the magnet is spinning in the presence of some conducting coils, the changing magnetic flux is going to induce electric currents in the coils. So this is something that we're going to be talking about in this chapter. All right. So now let's take a look at Faraday's law of induction. So basically, if you look at these three pictures here, so we have an ammeter that is used to measure current, and then we have a bar magnet. Now, in the first picture, the bar magnet is at rest; it's not moving. So when this is not moving, there is no current in these coils. Now notice that when the bar magnet is moved to the left, it induces a current in the coils, and you can see that the ammeter is going to show that there is a current in the wires. Now when the bar magnet is moved to the right, you see that the current becomes a positive value. So what this shows me is that I can use a magnetic field. So a changing magnetic field. So what is important here is the changing action. So when the magnet is at rest, there is no current, but the act of moving the magnet back and forth is what is important, and that is what is going to generate this current. So later on, we'll talk a little bit about the direction of the current, but again, you can see that when so in this example here, when the bar magnet is moved to the left, the current is induced in the clockwise direction, and when the bar magnet is moved to the right, the current is induced in the counterclockwise direction. So again, this is something that we're going to talk about just in a little bit. So we'll talk about the direction of this current. All right. So we can also think a little bit about Faraday's law of induction by looking at this example right here. So in this example, you have a power supply, and this is connected to some coils. So these are called the primary coils, and these are called the secondary coils. Now, when the switch in the primary coil is closed, the ammeter reading in the secondary coil changes. So again, when there is a current here, so when the switch is closed, there is a current that is going to go through this primary coil. Now the current in the coil is going to generate a magnetic field, and the magnetic field in this primary coil is going to induce a current in the secondary coil. Now this is just a very basic example here, but this is really the principle by which transformers operate. So this is really an example of a transformer right here. So you have the primary coil and you have the secondary coil. So you have some current going in the flowing through the primary coil. It's going to generate the magnetic field, and the magnetic field itself is then going to induce a current in the secondary coil. Now, so generally we can write down Faraday's law mathematically by means of this equation. So it says that the voltage, so the induced voltage or the induced electromotive force is given as the negative derivative of the magnetic flux as a function of time. So again, there is a reason why there is a negative sign here. We'll talk about this just in a little bit. Now, if you have not just a single loop of wire, but if you have a coil that is made up of n turns, then we need to multiply. So the electromotive force, we need to multiply that by n. So when there's n turns, then the voltage can be calculated using this equation. All right. Now we're going to talk a little bit about the magnetic flux. So we've already seen a little bit of this in chapter 29. But now suppose that we have a loop. So this is a loop of wire like this, and this is the so this loop has an area A, and there is a magnetic field that is going through the loop at some angle with respect to the normal vector. So if this is so the dotted line here shows me the normal vector of the loop. Then I can calculate my magnetic flux. So my magnetic flux is just the B, so the strength of the magnetic field times the cross-sectional area times the cosine of the angle between the directions of the magnetic field and the directions of the magnetic field and the directions of the unit vector to this area. So it means that I can calculate the electromotive force that is induced in this loop by taking the negative derivative of all of this quantity right here. All right, so this is a quick quiz. This is quick quiz number 30.1. I want you guys to take a look at this just to apply some concepts. Now we're going to look at example number 30.1. So in this example, it talks about inducing an electromotive force in a coil. So it says that suppose that you have a coil that has 200 turns of wire, and then it says that each turn is a square of side given by D equals to 18 centimeters. And then we know that a uniform magnetic field is directed perpendicular to the plane of the coil is turned on. Now the figure shows the behavior of the magnitude of the magnetic field with time. So from t equals to 0 to t equals to 8.0 seconds equals to 0.8 seconds, the field changes linearly from 0 to 0.5 Teslas. Now after t equals to 0.8 seconds, the magnitude of the field is going to decay in time according to this equation right here. So B equals to B max e to the negative 8 times t, where A is some constant and B max is equal to 0.5 Teslas. Now for part A, it's going to ask us what is the magnitude of the induced EMF in the coil between t equals to 0 and t equals to 0.8 seconds. So when I calculate the magnitude of the induced EMF, you just take the number of turns and you multiply by the change in the magnetic flux with respect to time. Now in this example, because the magnetic field is parallel to the area vector, the cosine of 0 is just equals to 1. So the magnetic flux is just the product of the strength of the magnetic field times the cross-sectional area. Now when I take when I calculate the change, notice that the area is not changing, but what is changing is the magnetic field. So it means that when I take this change here, it's different. So it's just given by n times a delta b over delta t. Now the area, because this is a square, the area is just d squared. And then I can say that the change in b over change in t is just b final minus b initial over change in time. So again, if you plug in the values right here, so n is equals to 200, b is equals to 0.18 meters. So you want to take that square, and then you multiply by the change in the magnetic field, divided by change in time. So the induced EMF, so the magnitude of the induced EMF is going to be 4.0 volt. So again, you want to notice that this EMF is produced because the magnetic field is changing. It's not constant. So it's this changing action, is the changing effect of the magnetic field that is responsible for inducing a voltage, an EMF. Now, what is the magnitude of the induced EMF in the coil after t equals to 0.8 seconds? So after t equals to 0.8 seconds, I need to use this equation right here. So when you calculate the magnitude, you can just say that. So you take the derivative of this quantity here. So taking the derivative here, you can pull out the area. The area is a constant. You can pull out B max. You take the derivative of this quantity here, e to the negative a times t. You get that. You plug in those values, you end up with this equation. So this is 3.2 times a times e to the negative a times t. So this is the expression for the magnitude of the induced EMF after t equals to 0.80 seconds. All right. Now, what if you were asked to find the magnitude of the induced current in the coil while the field is changing during the first 0.8 seconds? Can you answer that question? Yes. So again, we can calculate the current. So if we know the total resistance of the wire, which in this case is 2.0 ohms, then we can just calculate what the current that is going to flow in the wire is going to be given by the EMF over the resistance, which is 2.0 amps. So again, this is just Ohm's law. Now notice that what we're doing here is that we're just calculating the magnitude of the current. So we're not saying anything yet about the direction of the current.